This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Relativity, the Special and General Theory by Albert Einstein. Continuing Part 2, The General Theory of Relativity, Sections 27 to 29. Section 27. The space-time continuum of the general theory of relativity is not a Euclidean continuum. In the first part of this book, we were able to make use of space-time coordinates, which allowed of a simple and direct physical interpretation, and which, according to section 26, can be regarded as four-dimensional Cartesian coordinates. This was possible on the basis of the law of the constancy of the velocity of light. But according to section 21, the general theory of relativity cannot retain this law. On the contrary, we arrived at the result that according to this latter theory, the velocity of light must always depend on the coordinates when a gravitational field is present. In connection with a specific illustration in section 23, we found that the presence of a gravitational field invalidates the definition of the coordinates and the time, which led us to our objective in the special theory of relativity. In view of the results of these considerations, we are led to the conviction that, according to the general principle of relativity, the space-time continuum cannot be regarded as a Euclidean one, but that here we have the general case, corresponding to the marble slab with local variations of temperature, and with which we made acquaintance as an example of a two-dimensional continuum. Just as it was there impossible to construct a Cartesian coordinate system from equal rods, so here it is impossible to build up a system, or reference body, from rigid bodies and clocks, which shall be of such a nature that measuring rods and clocks, arranged rigidly with respect to one another, shall indicate position and time directly. Such was the essence of the difficulty with which we were confronted in section 23. But the considerations of section 25 and 26 show us the way to surmount this difficulty. We refer the four-dimensional space-time continuum in an arbitrary manner to Gauss coordinates. We assign to every point of the continuum, or event, four numbers, x sub 1, x sub 2, x sub 3, and x sub 4, coordinates, which have not the least direct physical significance, but only serve the purpose of numbering the points of the continuum in a definite but arbitrary manner. This arrangement does not even need to be of such a kind that we must regard x sub 1, x sub 2, and x sub 3 as space coordinates and x sub 4 as a time coordinate. The reader may think that such a description of the world would be quite inadequate. What does it mean to assign to an event the particular coordinates x sub 1, x sub 2, x sub 3, and x sub 4, if in themselves these coordinates have no significance? More careful consideration shows, however, that this anxiety is unfounded. Let us consider, for instance, a material point with any kind of motion. If this point had only a momentary existence without duration, then it would be described in space-time by a single system of values, x sub 1, x sub 2, x sub 3, and x sub 4. Thus its permanent existence must be characterized by an infinitely large number of such systems of values, the coordinate values of which are so close together as to give continuity. Corresponding to the material point, we thus have a unidimensional line in the four-dimensional continuum. In the same way, any such lines in our continuum correspond to many points in motion. The only statements having regard to these points which can claim a physical existence are in reality the statements about their encounters. In our mathematical treatment, such an encounter is expressed in the fact that the two lines which represent the motions of the points in question have a particular system of coordinate values, x sub 1, x sub 2, x sub 3 and x sub 4, in common. After mature consideration, the reader will doubtless admit that in reality such encounters constitute the only actual evidence of a time-space nature with which we meet in physical statements. When we were describing the motion of a material point relative to a body of reference, we stated nothing more than the encounters of this point with particular points of the reference body. We can also determine the corresponding values of the time by the observation of encounters of the body with clocks, in conjunction with the observation of the encounter of the hands of clocks with particular points on the dials. It is just the same in the case of space measurements by means of measuring rods, as a little consideration will show. The following statements hold generally. Every physical description resolves itself into a number of statements, each of which refers to the space-time coincidence of two events, A and B. In terms of Gaussian coordinates, every such statement is expressed by the agreement of their four coordinates, x sub 1, x sub 2, x sub 3 and x sub 4. Thus, in reality, the description of the time-space continuum by means of Gauss coordinates completely replaces the description with the aid of a body of reference, without suffering from the defects of the latter mode of description. It is not tied down to the Euclidean character of the continuum which has to be represented. Section 28. Exact formulation of the general principle of relativity. We are now in a position to replace the provisional formulation of the general principle of relativity given in section 18 by an exact formulation. The form there used, quote, "All bodies of reference, K, K', etc., are equivalent for the description of natural phenomena, or formulation of the general laws of nature, whatever may be their state of motion," unquote, cannot be maintained, because the use of rigid reference bodies, in the sense of the method followed in the special theory of relativity, is in general not possible in space-time description. The Gauss coordinate system has to take the place of the body of reference. The following statement corresponds to the fundamental idea of the general principle of relativity. All Gaussian coordinate systems are essentially equivalent for the formulation of the general laws of nature. We can state this general principle of relativity in still another form, which renders it yet more clearly intelligible than it is when in the form of the natural extension of the special principle of relativity. According to the special theory of relativity, the equations which express the general laws of nature pass over into equations of the same form when, by making use of the Lorentz transformation, we replace the space-time variables x, y, z and t of a Galilean reference body K by the space-time variables x', y', z' and t' of a new reference body K'. According to the general theory of relativity, on the other hand, by application of arbitrary substitutions of the Gauss variables x sub 1, x sub 2, x sub 3 and x sub 4, the equations must pass over into equations of the same form, for every transformation, not only the Lorentz transformation, corresponds to the transition of one Gauss coordinate system into another. If we desire to adhere to our old-time three-dimensional view of things, then we can characterize the development which is being undergone by the fundamental idea of the general theory of relativity as follows. The special theory of relativity has reference to Galilean domains, i.e. to those in which no gravitational field exists. In this connection, a Galilean reference body serves as body of reference, i.e. a rigid body the state of motion of which is so chosen that the Galilean law of the uniform rectilinear motion of isolated material points holds relatively to it. Certain considerations suggest that we should refer the same Galilean domains to non-Galilean reference bodies also. A gravitational field of a special kind is then present with respect to these bodies. Cf. sections 20 and 23. In gravitational fields there are no such things as rigid bodies with Euclidean properties. Thus the fictitious rigid body of reference is of no avail in the general theory of relativity. The motion of clocks is also influenced by gravitational fields, and in such a way that a physical definition of time, which is made directly with the aid of clocks, has by no means the same degree of plausibility as in the special theory of relativity. For this reason, non-rigid reference bodies are used, which are as a whole not only moving in any way whatsoever, but which also suffer alterations in form ad lib during their motion. Clocks, for which the law of motion is of any kind, however irregular, serve for the definition of time. We have to imagine each of these clocks fixed at a point on the non-rigid reference body. These clocks satisfy only the one condition, that the readings which are observed simultaneously on adjacent clocks in space differ from each other by an indefinitely small amount. This non-rigid reference body, which might appropriately be termed a reference mollusc, is in the main equivalent to a Gaussian four-dimensional coordinate system chosen arbitrarily. That which gives the mollusc a certain comprehensibility as compared with the Gauss coordinate system is the really unjustified formal retention of the separate existence of the space coordinates as opposed to the time coordinate. Every point on the mollusc is treated as a space point, and every material point which is at rest relatively to it is at rest, so long as the mollusc is considered as reference body. The general principle of relativity requires that all these molluscs can be used as reference bodies, with equal right and equal success in the formulation of the general laws of nature. The laws themselves must be quite independent of the choice of mollusc. The great power possessed by the general principle of relativity lies in the comprehensive limitation which is imposed on the laws of nature in consequence of what we have seen above. Section 29. The solution of the problem of gravitation on the basis of the general principle of relativity. If the reader has followed all our previous considerations, he will have no further difficulty in understanding the methods leading to the solution of the problem of gravitation. We start off on a consideration of a Galilean domain, i.e. a domain in which there is no gravitational field relative to the Galilean reference body K. The behaviour of measuring rods and clocks with reference to K is known from the special theory of relativity. Likewise the behaviour of isolated material points. The latter move uniformly and in straight lines. Now let us refer this domain to a random Gauss coordinate system or to a mollusc as reference body K'. Then, with respect to K', there is a gravitational field G of a particular kind. We learn the behaviour of measuring rods and clocks, and also of freely moving material points with reference to K', simply by mathematical transformation. We interpret this behaviour as the behaviour of measuring rods, clocks, and material points under the influence of the gravitational field G. Hereupon we introduce a hypothesis, that the influence of the gravitational field on measuring rods, clocks, and freely moving material points continues to take place according to the same laws, even in the case where the prevailing gravitational field is not derivable from the Galilean special case, simply by means of a transformation of coordinates. The next step is to investigate the space-time behavior of the gravitational field G, which was derived from the Galilean special case simply by transformation of the coordinates. This behavior is formulated in a law, which is always valid, no matter how the reference body, or mollusc, used in the description may be chosen. This law is not yet the general law of the gravitational field, since the gravitational field under consideration is of a special kind. In order to find out the general law of field of gravitation, we still require to obtain a generalization of the law as found above. This can be obtained without caprice, however, by taking into consideration the following demands. A. The required generalization must likewise satisfy the general postulate of relativity. B. If there is any matter in the domain under consideration, only its inertial mass, and thus according to section 15, only its energy is of importance for its effect in exciting a field. C. Gravitational field and matter together must satisfy the law of the conservation of energy and of impulse. Finally, the general principle of relativity permits us to determine the influence of the gravitational field on the course of all those processes which take place according to known laws when a gravitational field is absent, i.e., which have already been fitted into the frame of the special theory of relativity. In this connection, we proceed in principle according to the method which has already been explained for measuring rods, clocks, and freely moving material points. The theory of gravitation derived in this way from the general postulate of relativity excels not only in its beauty, nor in removing the defect attaching to classical mechanics, which was brought to light in section 21, nor in interpreting the empirical law of the equality of inertial and gravitational mass, but it has also already explained a result of observation in astronomy, against which classical mechanics is powerless. If we confine the application of the theory to the case where the gravitational fields can be regarded as being weak, and in which all masses move with respect to the coordinate system with velocities which are small compared with the velocity of light, we then obtain as a first approximation the Newtonian theory. Thus the latter theory is obtained here without any particular assumption, whereas Newton had to introduce the hypothesis that the force of attraction between mutually attracting material points is inversely proportional to the square of the distance between them. If we increase the accuracy of the calculation, deviations from the theory of Newton make their appearance, practically all of which must nevertheless escape the test of observation owing to their smallness. We must draw attention here to one of these deviations. According to Newton's theory, a planet moves around the Sun in an ellipse, which would permanently maintain its position with respect to the fixed stars, if we could disregard the motion of the fixed stars themselves and the action of the other planets under consideration. Thus, if we correct the observed motion of the planets for these two influences, and if Newton's theory be strictly correct, we ought to obtain for the orbit of the planet an ellipse, which is fixed with reference to the fixed stars. This deduction, which can be tested with great accuracy, has been confirmed for all the planets save one, with the precision that is capable of being obtained by the delicacy of observation attainable at the present time. The sole exception is Mercury, the planet which lies nearest the Sun. Since the time of Leverrier, it has been known that the eclipse corresponding to the orbit of Mercury, after it has been corrected for the influences mentioned above, is not stationary with respect to the fixed stars, but that it rotates exceedingly slowly in the plane of the orbit and in the sense of the orbital motion. The value obtained for this rotary movement of the orbital ellipse was 43 seconds of arc per century, an amount ensured to be correct to within a few seconds of arc. This effect can be explained by means of classical mechanics only on the assumption of hypotheses which have little probability, and which were devised solely for this purpose. On the basis of the general theory of relativity, it is found that the ellipse of every planet round the sun must necessarily rotate in the manner indicated above; that for all the planets, with the exception of Mercury, this rotation is too small to be detected with the delicacy of observation possible at the present time, but that in the case of Mercury it must amount to 43 seconds of arc per century, a result which is strictly in agreement with observation. Apart from this one, it has hitherto been possible to make only two deductions from the theory which admit of being tested by observation, to wit, the curvature of light rays by the gravitational field of the sun, first observed by Eddington and others in 1919, and a displacement of the spectral lines of light reaching us from large stars, as compared with the corresponding lines for light produced in an analogous manner terrestrially, i.e. by the same kind of atom, established by Adams in 1924. These two deductions from the theory have both been confirmed. End of section 29.
Correction for this chapter. In mathematical formulae, instead of I, hear 1.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Liu. Relativity, the Special and General Theory, by Albert Einstein. Continuing Part 1, Sections 13 through 15. Section 13. Theorem of the addition of velocities, the experiment of Fizeau. Now in practice we can move clocks and measuring rods only with velocities that are small compared with the velocity of light. Hence we shall hardly be able to compare the results of the previous section directly with the reality. But on the other hand, these results must strike you as being very singular, and for that reason I shall now draw another conclusion from the theory, one which can easily be derived from the foregoing considerations, and which has been most elegantly confirmed by experiment. In Section 6 we derive the theorem of the addition of velocities in one direction in the form which also results from the hypotheses of classical mechanics. This theorem can also be deduced readily from the Galilei transformation, Section 11. In place of the man walking inside the carriage, we introduce a point moving relatively to the coordinate system K' in accordance with the equation x' equals wt'. By means of the first and fourth equations of the Galilei transformation, we can express x' and t' in terms of x and t, and we then obtain x equals (v plus w) t. This equation expresses nothing else than the law of motion of the point with reference to the system K, of the man with reference to the embankment. We denote this velocity by the symbol W, and we then obtain, as in Section 6, W equals v plus w, equation A. But we can carry out this consideration just as well on the basis of the theory of relativity. In the equation x' equals wt', we must then express x' and t' in terms of x and t, making use of the first and fourth equations of the Lorentz transformation. Instead of the equation A, we then obtain the equation W equals the sum v plus w over the sum I plus vw over c squared. Equation B, which corresponds to the theorem of addition for velocities in one direction according to the theory of relativity. The question now arises as to which of these two theorems is the better in accord with experience. On this point we are enlightened by a most important experiment which the brilliant physicist Fizeau performed more than half a century ago, and which has been repeated since then by some of the best experimental physicists, so that there can be no doubt about its result. The experiment is concerned with the following question. Light travels in a motionless liquid with a particular velocity w. How quickly does it travel in the direction of the arrow in the tube T? See the accompanying diagram, Fig. 3. When the liquid above mentioned is flowing through the tube with a velocity v. In accordance with the principle of relativity, we shall certainly have to take for granted that the propagation of light always takes place with the same velocity w with respect to the liquid, whether the latter is in motion with reference to other bodies or not. The velocity of light relative to the liquid and the velocity of the latter relative to the tube are thus known, and we require the velocity of light relative to the tube. It is clear that we have the problem of section 6 again before us. The tube plays a part of the railway embankment, or of the coordinate system K. The liquid plays a part of the carriage, or of the coordinate system K', and finally the light plays a part of the man walking along the carriage, or of the moving point in the present section. If we denote the velocity of the light relative to the tube by capital W, then this is the given by the equation A or B. According as the Galilei transformation or the Lorentz transformation corresponds to the facts. Experiment decides in favor of equation B derived from the theory of relativity, and the agreement is, indeed, very exact. Footnote: Fizeau found W equals W plus V open parentheses I minus I over n squared close parentheses, where n equals C over W is the index of refraction of the liquid. On the other hand, owing to the smallness of VW over C squared as compared with I, we can replace B in the first place by capital W equals open parentheses W plus V close parentheses open parentheses I minus the fraction VW over C squared close parentheses, or to the same order of approximation by W plus V open parentheses I minus I over n squared close parentheses, which agrees with Fizeau's result. End footnote. According to recent and most excellent measurements by Zeeman, the influence of the velocity of flow v on the propagation of light is represented by formula B to within 1%. Nevertheless, we must now draw attention to the fact that a theory of this phenomenon was given by H. A. Lorentz long before the statement of the theory of relativity. This theory was of a purely electrodynamical nature, and was obtained by the use of particular hypotheses as to the electromagnetic structure of matter. This circumstance, however, does not in the least diminish the conclusiveness of the experiment as a crucial test in favor of the theory of relativity, for the electrodynamics of Maxwell-Lorentz, on which the original theory was based, in no way opposes the theory of relativity. Rather has the latter been developed from electrodynamics as an astoundingly simple combination and generalization of the hypotheses, formally independent of each other, on which electrodynamics was built. End of section 13. Section 14. The heuristic value of the theory of relativity. Our train of thought in the foregoing pages can be epitomized in the following manner. Experience has led to the conviction that, on the one hand, the principle of relativity holds true, and that on the other hand, the velocity of transmission of light in vacuo has to be considered equal to a constant c. By uniting these two postulates, we obtain the law of transformation for the rectangular coordinates x, y, z, and the time t of the events which constitute the processes of nature. In this connection we did not obtain the Galilei transformation, but, differing from classical mechanics, the Lorentz transformation. The law of transmission of light, the acceptance of which is justified by our actual knowledge, played an important part in this process of thought. Once in possession of the Lorentz transformation, however, we can combine this with the principle of relativity and sum up the theory thus. Every general law of nature must be so constituted that it is transformed into a law of exactly the same form when, instead of the space-time variables x, y, z, t of the original coordinate system K, we introduce new space-time variables x', y', z', t' of a coordinate system K'. In this connection the relation between the ordinary and the accented magnitudes is given by the Lorentz transformation, or in brief, general laws of nature are covariant with respect to Lorentz transformation. This is a definite mathematical condition that the theory of relativity demands of a natural law, and in virtue of this, the theory becomes a valuable heuristic aid in the search for general laws of nature. If a general law of nature were to be found which did not satisfy this condition, then at least one of the two fundamental assumptions of the theory would have been disproved. Let us now examine what general results the latter theory has hitherto evinced. End of section 14. Section 15. General results of the theory. It is clear from our previous considerations that the special theory of relativity has grown out of electrodynamics and optics. In these fields it has not appreciably altered the predictions of theory, but it has considerably simplified the theoretical structure, i.e. the derivation of laws, and, what is incomparably more important, it has considerably reduced the number of independent hypotheses forming the basis of theory. The special theory of relativity has rendered the Maxwell-Lorentz theory so plausible that the latter would have been generally accepted by physicists, even if experiment had decided less unequivocally in its favor. Classical mechanics required to be modified before it could come into line with the demands of the special theory of relativity. For the main part, however, this modification affects only the laws for rapid motions, in which the velocities of matter v are not very small as compared with the velocity of light. We have experience of such rapid motions only in the case of electrons and ions. For other motions, the variations from the laws of classical mechanics are too small to make themselves evident in practice. We shall not consider the motion of stars until we come to speak of the general theory of relativity. In accordance with the theory of relativity, the kinetic energy of a material point of mass m is no longer given by the well-known expression m v²/2, but by the expression mc² over the square root of the difference I minus the fraction v²/c². If this expression approaches infinity, as the velocity v approaches the velocity of light c, the velocity must therefore always remain less than c, however great may be the energies used to produce the acceleration. If we develop the expression for the kinetic energy in the form of a series, we obtain mc² plus m v²/2 plus 3a m v⁴/c² plus etc. When v²/c² is small compared with unity, the third of these terms is always small in comparison with the second, which last is alone considered in classical mechanics. The first term mc² does not contain the velocity, and requires no consideration if we are only dealing with a question as to how the energy of a point mass depends on the velocity. We shall speak of its essential significance later. The most important result of a general character to which the special theory of relativity has led is concerned with the conception of mass. Before the advent of relativity, physics recognized two conservation laws of fundamental importance, namely, the law of conservation of energy and the law of the conservation of mass. These two fundamental laws appeared to be quite independent of each other. By means of the theory of relativity, they have been united into one law. We shall now briefly consider how this unification came about, and what meaning is to be attached to it. The principle of relativity requires that the law of the conservation of energy should hold not only with reference to a coordinate system K, but also with respect to every coordinate system K', which is in a state of uniform motion of translation relative to K, or, briefly, relative to every Galilean system of coordinates. In contrast to classical mechanics, the Lorentz transformation is the deciding factor in the transition from one such system to another. By means of comparatively simple considerations, we are led to draw the following conclusions from these premises. In conjunction with the fundamental equations of the electrodynamics of Maxwell, a body moving with a velocity v which absorbs footnote 1. E sub 0 is the energy taken up, as judged from a coordinate system moving with a body. End footnote. An amount of energy E sub 0 in the form of radiation, without suffering an alteration in velocity in the process, has as a consequence its energy increased by an amount E sub 0 over the square root of the difference I minus v squared over c squared. In consideration of the expression given above for the kinetic energy of the body, the required energy of the body comes out to be the sum m plus E sub 0 over c squared times c squared over the square root of the difference I minus v squared over c squared. Thus the body has the same energy as a body of mass, m plus E sub 0 over c squared, moving with a velocity v. Hence we can say, if a body takes up an amount of energy E sub 0, then its inertial mass increases by an amount E sub 0 over c squared. The inertial mass of a body is not a constant, but varies according to the change in the energy of the body. The inertial mass of a system of bodies can even be regarded as a measure of its energy. The law of the conservation of the mass of a system becomes identical with the law of the conservation of energy, and is only valid provided that the system neither takes up nor sends out energy, writing the expression for the energy in the form the sum mc squared plus E sub 0 over the square root of the difference I minus v squared over c squared. We see that the term mc squared, which has hitherto attracted our attention, is nothing else than the energy possessed by the body. Footnote 2. As judged from a coordinate system moving with a body. End footnote. Before it absorbed the energy E sub 0. A direct comparison of this relation with experiment is not possible at the present time. Note: the equation E equals mc squared has been thoroughly proved time and again since this time. End note. Owing to the fact that the changes in energy E0 to which we can subject a system are not large enough to make themselves perceptible as a change in the inertial mass of the system, E0 over c squared is too small in comparison with the mass m, which was present before the alteration of the energy. It is owing to this circumstance that classical mechanics was able to establish successfully the conservation of mass as a law of independent validity. Let me add a final remark of a fundamental nature. the success of the Faraday-Maxwell interpretation of electromagnetic action at a distance resulted in physicists becoming convinced that there are no such things as instantaneous actions at a distance, not involving an intermediary medium, of the type of Newton's law of gravitation. According to the theory of relativity, action at a distance with the velocity of light always takes the place of instantaneous action at a distance, or of action at a distance with an infinite velocity of transmission. This is connected with the fact that the velocity c plays a fundamental role in this theory. In Part II, we shall see in what way this result becomes modified in the general theory of relativity. End of section 15.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Peter Eastman, July 30th, 2006. Relativity, the Special and General Theory by Albert Einstein. Continuing Part 1. Section 7. The apparent incompatibility of the law of propagation of light with the principle of relativity. There is hardly a simpler law in physics than that according to which light is propagated in empty space. Every child at school knows, or believes he knows, that this propagation takes place in straight lines with the velocity c equals 300,000 kilometers per second. At all events, we know with great exactness that this velocity is the same for all colors, because if this were not the case, the minimum of emission would not be observed simultaneously for different colors during the eclipse of a fixed star by its dark neighbor. By means of similar considerations, based on observations of double stars, the Dutch astronomer De Sitter was also able to show that the velocity of propagation of light cannot depend on the velocity of motion of the body emitting the light. The assumption that this velocity of propagation is dependent on the direction in space is in itself improbable. In short, let us assume that the simple law of the constancy of the velocity of light c in vacuum is justifiably believed by the child at school. Who would imagine that this simple law has plunged the conscientiously thoughtful physicist into the greatest intellectual difficulties? Let us consider how these difficulties arise. Of course we must refer the process of the propagation of light, and indeed every other process, to a rigid reference body, coordinate system. As such a system, let us again choose our embankment. We shall imagine the air above it to have been removed. If a ray of light be sent along the embankment, we see from the above that the tip of the ray will be transmitted with the velocity c relative to the embankment. Now, let us suppose that our railway carriage is again traveling along the railway lines with the velocity v, and that its direction is the same as that of the ray of light, but its velocity, of course, much less. Let us inquire about the velocity of propagation of the ray of light relative to the carriage. It is obvious that we can here apply the consideration of the previous section, since the ray of light plays the part of the man walking along relatively to the carriage. The velocity W of the man relative to the embankment is here replaced by the velocity of light relative to the embankment. W is the required velocity of light with respect to the carriage, and we have W equals c minus v. The velocity of propagation of a ray of light relative to the carriage thus comes out smaller than c. But this result comes into conflict with the principle of relativity set forth in section 5. For like every other general law of nature, the law of the transmission of light in vacuo must, according to the principle of relativity, be the same for the railway carriage as reference body as when the rails are the body of reference. But from our above consideration, this would appear to be impossible. If every ray of light is propagated relative to the embankment with the velocity c, then for this reason it would appear that another law of propagation of light must necessarily hold with respect to the carriage, a result contradictory to the principle of relativity. In view of this dilemma, there appears to be nothing else for it than to abandon either the principle of relativity or the simple law of the propagation of light in vacuo. Those of you who have carefully followed the preceding discussion are almost sure to expect that we should retain the principle of relativity, which appeals so convincingly to the intellect because it is so natural and simple. The law of the propagation of light in vacuo would then have to be replaced by a more complicated law, conformable to the principle of relativity. The development of theoretical physics shows, however, that we cannot pursue this course. The epoch-making theoretical investigations of H.A. Lorentz on the electrodynamical and optical phenomena connected with moving bodies show that experience in this domain leads conclusively to a theory of electromagnetic phenomena, of which the law of the constancy of the velocity of light in vacuo is a necessary consequence. Prominent theoretical physicists were therefore more inclined to reject the principle of relativity, in spite of the fact that no empirical data had been found which were contradictory to this principle. At this juncture, the theory of relativity entered the arena. As a result of an analysis of the physical conceptions of time and space, it became evident that in reality there is not the least incompatibility between the principle of relativity and the law of propagation of light, and that by systematically holding fast to both these laws, a logically rigid theory could be arrived at. This theory has been called the special theory of relativity, to distinguish it from the extended theory, with which we shall deal later. In the following pages we shall present the fundamental ideas of the special theory of relativity. End of section 7. Section 8. On the idea of time in physics. Lightning has struck the rails on a railway embankment at two places, A and B, far distant from each other. I make the additional assertion that these two lightning flashes occurred simultaneously. If I ask you whether there is sense in this statement, you will answer my question with a decided yes. But if I now approach you with a request to explain to me the sense of the statement more precisely, you find after some consideration that the answer to this question is not so easy as it appears at first sight. After some time, perhaps the following answer would occur to you. The significance of the statement is clear in itself and needs no further explanation. Of course, it would require some consideration if I were to be commissioned to determine by observations whether in the actual case the two events took place simultaneously or not. I cannot be satisfied with this answer, for the following reason. Supposing that as a result of ingenious considerations, an able meteorologist were to discover that the lightning must always strike the places A and B simultaneously. Then we should be faced with the task of testing whether or not this theoretical result is in accordance with the reality. We encounter the same difficulty with all physical statements in which the conception simultaneous plays a part. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled in an actual case. We thus require a definition of simultaneity, such that this definition supplies us with the method by means of which, in the present case, he can decide by experiment whether or not both the lightning strokes occurred simultaneously. As long as this requirement is not satisfied, I allow myself to be deceived as a physicist, and, of course, the same applies if I am not a physicist, when I imagine that I am able to attach a meaning to the statement of simultaneity. I would ask the reader not to proceed farther until he is fully convinced on this point. After thinking the matter over for some time, you then offer the following suggestion with which to test simultaneity. By measuring along the rails, the connecting line AB should be measured up, and an observer placed at the midpoint M of the distance AB. This observer should be supplied with an arrangement, e.g. 2 mirrors inclined at 90 degrees, which allows him visually to observe both places A and B at the same time. If the observer perceives the 2 flashes of lightning at the same time, then they are simultaneous. I am very pleased with the suggestion, but for all that, I cannot regard the matter as quite settled, because I feel constrained to raise the following objection. Your definition would certainly be right if only I knew that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. But an examination of this supposition would only be possible if we already had at our disposal the means of measuring time. It would thus appear as though we were moving here in a logical circle. After further consideration, you cast a somewhat disdainful glance at me, and rightly so. And you declare, I maintain my previous definition nevertheless, because in reality it assumes absolutely nothing about light. There is only one demand to be made of the definition of simultaneity, namely, that in every real case it must supply us with an empirical decision as to whether or not the conception that has to be defined is fulfilled. That my definition satisfies this demand is indisputable. That light requires the same time to traverse the path A to M as for the path B to M is in reality neither a supposition nor a hypothesis about the physical nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. It is clear that this definition can be used to give an exact meaning not only to 2 events, but to as many events as we care to choose, and independently of the positions of the scenes of the events with respect to the body of reference, here the railway embankment. Footnote. We suppose further that when 3 events, A, B, and C, occur in different places in such a manner that A is simultaneous with B, and B is simultaneous with C, simultaneous in the sense of the above definition, then the criterion for the simultaneity of the pair of events A, C is also satisfied. This assumption is a physical hypothesis about the propagation of light. It must certainly be fulfilled if we are to maintain the law of the constancy of the velocity of light in vacuo. End of footnote. We are thus led also to a definition of time in physics. For this purpose, we suppose that clocks of identical construction are placed at the points A, B, and C of the railway line coordinate system, and that they are set in such a manner that the positions of their pointers are simultaneously, in the above sense, the same. Under these conditions, we understand by the time of an event the reading, position of the hands, of that one of these clocks which is in the immediate vicinity in space of the event. In this manner, a time value is associated with every event which is essentially capable of observation. This stipulation contains a further physical hypothesis, the validity of which will hardly be doubted without empirical evidence to the contrary. It has been assumed that all these clocks go at the same rate, if they are of identical construction. Stated more exactly, when two clocks arranged at rest in different places of a reference body are set in such a manner that a particular position of the pointers of the one clock is simultaneous, in the above sense, with the same position of the pointers of the other clock, then identical settings are always simultaneous, in the sense of the above definition. End of section 8. Section 9. The Relativity of Simultaneity. Up to now, our considerations have been referred to a particular body of reference, which we have styled a railway embankment. We suppose a very long train traveling along the rails with the constant velocity v, and in the direction indicated in Figure 1. People traveling in this train will, with advantage, view the train as a rigid reference body, coordinate system. They regard all events in reference to the train. Then, every event which takes place along the line also takes place at a particular point of the train. Also, the definition of simultaneity can be given relative to the train in exactly the same way as with respect to the embankment. As a natural consequence, however, the following question arises. Are two events, e.g. the two strokes of lightning A and B, which are simultaneous with reference to the railway embankment, also simultaneous relatively to the train? We shall show directly that the answer must be in the negative. When we say that the lightning strokes A and B are simultaneous with respect to the embankment, we mean the rays of light emitted at the places A and B where the lightning occurs meet each other at the midpoint M of the length A to B of the embankment. But the events A and B also correspond to positions A and B on the train. Let M' be the midpoint of the distance A to B on the traveling train. Just when the flashes, as judged from the embankment, of lightning occur, this point M' naturally coincides with the point M, but it moves toward the right in the diagram with the velocity v of the train. If an observer sitting at the position M' in the train did not possess this velocity, then he would remain permanently at M, and the light rays emitted by the flashes of lightning A and B would reach him simultaneously, i.e., they would meet just where he is situated. Now, in reality, considered with reference to the railway embankment, he is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Hence, the observer will see the beam of light emitted from B earlier than he will see that emitted from A. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. We thus arrive at an important result. Events which are simultaneous with reference to the embankment are not simultaneous with respect to the train, and vice versa. Relativity of simultaneity. Every reference body, coordinate system, has its own particular time. Unless we are told the reference body to which the statement of time refers, there is no meaning in a statement of the time of an event. Now, before the advent of the theory of relativity, it had always tacitly been assumed in physics that the statement of time had an absolute significance, i.e., that it is independent of the state of motion of the body of reference. But we have just seen that this assumption is incompatible with the most natural definition of simultaneity. If we discard this assumption, then the conflict between the law of the propagation of light in vacuo and the principle of relativity, developed in section 7, disappears. We were led to that conflict by the considerations of section 6, which are now no longer tenable. In that section, we concluded that the man in the carriage, who traverses the distance w per second relative to the carriage, traverses the same distance also with respect to the embankment in each second of time. But according to the foregoing considerations, the time required by a particular occurrence with respect to the carriage must not be considered equal to the duration of the same occurrence as judged from the embankment as reference body. Hence, it cannot be contended that the man in walking travels the distance w relative to the railway line in a time which is equal to 1 second, as judged from the embankment. Moreover, the considerations of section 6 are based on yet a second assumption, which in the light of a strict consideration appears to be arbitrary, although it was always tacitly made, even before the introduction of the theory of relativity. End of section 9.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Linda Liu. Relativity, the Special and General Theory, by Albert Einstein. Part 3. Considerations on the Universe as a Whole. Sections 30, 31, and 32. Section 30. Cosmological difficulties of Newton's theory. Apart from the difficulty discussed in section 21, there is a second fundamental difficulty attending classical celestial mechanics, which, to the best of my knowledge, was first discussed in detail by the astronomer Seeliger. If we ponder over the question as to how the universe, considered as a whole, is to be regarded, the first answer that suggests itself to us is surely this: as regards space and time, the universe is infinite. There are stars everywhere, so that the density of matter, although very variable in detail, is nevertheless on the average everywhere the same. In other words, however far we might travel through space, we should find everywhere an attenuated swarm of fixed stars of approximately the same kind and density. This view is not in harmony with the theory of Newton. The latter theory rather requires that the universe should have a kind of center in which the density of the stars is a maximum, and that as we proceed outwards from this center, the group density of the stars should diminish, until finally, at great distances, it is succeeded by an infinite region of emptiness. The stellar universe ought to be a finite island in the infinite ocean of space. Begin footnote. Proof. According to the theory of Newton, the number of lines of force which come from infinity and terminate in a mass m is proportional to the mass m. If, on the average, the mass density rho sub 0 is constant throughout the universe, then a sphere of volume v will enclose the average man, rho sub 0 v. Thus the number of lines of force passing through the surface f of the sphere into its interior is proportional to rho sub 0 v. For unit area of the surface of the sphere, the number of lines of force which enters the sphere is thus proportional to rho sub 0 v over f, or to rho sub 0 r. Hence the intensity of the field at the surface would ultimately become infinite with increasing radius r of the sphere, which is impossible. End footnote. This conception is in itself not very satisfactory. It is still less satisfactory because it leads to the result that the light emitted by the stars and also individual stars of the stellar system are perpetually passing out into infinite space, never to return and without ever again coming into interaction with other objects of nature. Such a finite material universe would be destined to become gradually but systematically impoverished. In order to escape this dilemma, Seeliger suggested a modification of Newton's law, in which he assumes that for great distances the force of attraction between two masses diminishes more rapidly than would result from the inverse square law. In this way, it is possible for the mean density of matter to be constant everywhere, even to infinity, without infinitely large gravitational fields being produced. We thus free ourselves from the distasteful conception that the material universe ought to possess something of the nature of a center. Of course, we purchase our emancipation from the fundamental difficulties mentioned at the cost of a modification and complication of Newton's law, which has neither empirical nor theoretical foundation. We can imagine innumerable laws which would serve the same purpose, without our being able to state a reason why one of them is to be preferred to the others, for any one of these laws would be founded just as little on more general theoretical principles as is the law of Newton. End of section 30. Section 31. The possibility of a finite and yet unbounded universe. But speculations on the structure of the universe also move in quite another direction. The development of non-Euclidean geometry led to the recognition of the fact that we can cast doubt on the infiniteness of our space without coming into conflict with the laws of thought or with experience. Riemann, Helmholtz. These questions have already been treated in detail and with unsurpassable lucidity by Helmholtz and Poincaré, whereas I can only touch on them briefly here. In the first place, we imagine an existence in two-dimensional space. Flat beings with flat implements, and in particular, flat rigid measuring rods, are free to move in a plane. For them, nothing exists outside of this plane. That which they observe to happen to themselves and to their flat things is the all-inclusive reality of their plane. In particular, the constructions of plane Euclidean geometry can be carried out by means of the rods. For example, the lattice construction considered in section 24. In contrast to ours, the universe of these beings is two-dimensional, but, like ours, it extends to infinity. In their universe, there is room for an infinite number of identical squares made up of rods, i.e., its volume, surface, is infinite. If these beings say their universe is, quote, plane, unquote, there is sense in this statement, because they mean that they can perform the constructions of plane Euclidean geometry with their rods. In this connection, the individual rods always represent the same distance, independently of their position. Let us consider now a second two-dimensional existence, but this time on a spherical surface instead of on a plane. The flat beings with their measuring rods and other objects fit exactly on this surface. They are unable to leave it. Their whole universe of observation extends exclusively over the surface of the sphere. Are these beings able to regard the geometry of their universe as being plane geometry, and their rods withal as a realization of distance? They cannot do this, for if they attempt to realize a straight line, they will obtain a curve, which we three-dimensional beings designate as a great circle, i.e., a self-contained line of definite finite length, which can be measured up by means of a measuring rod. Similarly, this universe has a finite area that can be compared with the area of a square constructed with rods. great charm resulting from this consideration lies in the recognition of the fact that the universe of these beings is finite and yet has no limits. But the spherical surface beings do not need to go on a world tour in order to perceive that they are not living in a Euclidean universe. They can convince themselves of this on every part of their world, provided they do not use too small a piece of it. Starting from a point, they draw straight lines, arcs of circles as judged in three-dimensional space, of equal length in all directions. They will call the line joining the free ends of these lines a circle. For a plane surface, the ratio of the circumference of a circle to its diameter, both lengths being measured with the same rod, is, according to Euclidean geometry of the plane, equal to a constant value pi, which is independent of the diameter of the circle. On their spherical surface, our flat beings would find for this ratio the value, equation 27, pi times sine, parentheses, little r over big R, parentheses, divided by, parentheses, little r over big R, parentheses, i.e. smaller value than pi, the difference being the more considerable, greater is the radius of the circle in comparison with the radius r of the world sphere. By means of this relation, spherical beings can determine the radius of their universe, quote, world, unquote, even when only a relatively small part of their world sphere is available for their measurements. But if this part is very small indeed, they will no longer be able to demonstrate that they are on a spherical world and not on a Euclidean plane, for a small part of a spherical surface differs only slightly from a piece of a plane of the same size. Thus, if the spherical surface beings are living on a planet of which the solar system occupies only a negligibly small part of the spherical universe, they have no means of determining whether they are living in a finite or an infinite universe, because a piece of universe to which they have access is in both cases practically plane, or Euclidean. It follows directly from this discussion that for our sphere beings, the circumference of a circle first increases with the radius until the circumference of the universe is reached, and that it thenceforward gradually decreases to zero for still further increasing values of the radius. During this process, the area of the circle continues to increase more and more, until finally it becomes equal to the total area of the whole world sphere. Perhaps the reader will wonder why we have placed our beings on a sphere rather than on another closed surface. But this choice has its justifications in the fact that, of all closed surfaces, the sphere is unique in possessing the property that all points on it are equivalent. I admit that the ratio of the circumference c of a circle to its radius r depends on r, but for a given value of r, it is the same for all points of the world sphere. In other words, the world sphere is a surface of constant curvature. To this two-dimensional sphere universe, there is a three-dimensional analogy, namely, the three-dimensional spherical space which was discovered by Riemann. Its points are likewise all equivalent. It possesses a finite volume which is determined by its radius, 2 pi squared r cubed. Is it possible to imagine a spherical space? To imagine a space means nothing else than that we imagine an epitome of our space experience, i.e. of experience that we can have in the movement of rigid bodies. In this sense, we can imagine a spherical space. Suppose we draw lines or stretch strings in all directions from a point, and mark off from each of these the distance r with a measuring rod. All the free ends of these lengths lie on a spherical surface. We can specially measure up the area f of the surface by means of a square made up of measuring rods. If the universe is Euclidean, then F equals 4 pi r squared. If it is spherical, then F is always less than 4 pi r squared. With increasing values of r, F increases from 0 up to a maximum value which is determined by the world radius. But for still further increasing values of r, the area gradually diminishes to 0. At first, the straight lines which radiate from the starting point diverge farther and farther from one another, but later they approach each other, and finally they run together again at a "counterpoint" to the starting point. Under such conditions, they have traversed the whole spherical space. It is easily seen that the three-dimensional spherical space is quite analogous to the two-dimensional spherical surface. It is finite, i.e., a finite volume, and has no bounds. It may be mentioned that there is yet another kind of curved space, elliptical space. It can be regarded as a curved space in which the two counterpoints are identical, indistinguishable from each other. An elliptical universe can thus be considered, to some extent, as a curved universe possessing central symmetry. It follows from what has been said that closed spaces without limits are conceivable. From amongst these, the spherical space and the elliptical excels in its simplicity, since all points on it are equivalent. As a result of this discussion, a most interesting question arises for astronomers and physicists, and that is whether the universe in which we live is infinite, or whether it is finite in the manner of the spherical universe. Our experience is far from being sufficient to enable us to answer this question, but the general theory of relativity permits of our answering it with a moderate degree of certainty. And in this connection, the difficulty mentioned in section 30 finds its solution. End of section 31. Section 32. Structure of space according to the general theory of relativity. According to the general theory of relativity, the geometrical properties of space are not independent, but they are determined by matter. Thus we can draw conclusions about the geometrical structure of the universe only if we base our considerations on the state of the matter as being something that is known. We know from experience that for a suitably chosen coordinate system, the velocities of the stars are small as compared with the velocity of transmission of light. We can thus, as a rough approximation, arrive at a conclusion as to the nature of the universe as a whole if we treat the matter as being at rest. We already know from our previous discussion that the behavior of measuring rods and clocks is influenced by gravitational fields, i.e., by the distribution of matter. This in itself is sufficient to exclude the possibility of the exact validity of Euclidean geometry in our universe. But it is conceivable that our universe differs only slightly from a Euclidean one, and this notion seems all the more probable since calculations show that the metrics of surrounding space is influenced only to an exceedingly small extent by masses even of the magnitude of our Sun. We might imagine that, as regards geometry, our universe behaves analogously to a surface which is irregularly curved in its individual parts, but which nowhere departs appreciably from a plane, something like the rippled surface of a lake. Such a universe might fittingly be called a quasi-Euclidean universe. As regards its space, it would be infinite, but calculation shows that in a quasi-Euclidean universe the average density of matter would necessarily be nil. Thus such a universe could not be inhabited by matter everywhere. It would present to us that unsatisfactory picture which we portrayed in section 30. If we are to have in the universe an average density of matter which differs from zero, however small may be that difference, then the universe cannot be quasi-Euclidean. On the contrary, the results of calculation indicate that if matter be distributed uniformly, the universe would necessarily be spherical or elliptical. Since in reality the detailed distribution of matter is not uniform, the real universe will deviate in individual parts from the spherical, i.e. the universe will be quasi-spherical, but it will be necessarily finite. In fact, the theory supplies us with a simple connection. Footnote. For the radius r of the universe, we obtain the equation r squared equals 2 over kappa rho. The use of the CGS system in this equation gives 2 over k equals 1 to the 8th power times 10 to the 27th power. P is the average density of the matter, and k is a constant connected with the Newtonian constant of gravitation. End footnote. Between the space expanse of the universe and the average density of matter in it. End section 32. End of part 3. End of Relativity, Special and General Theory by Albert Einstein.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Annie Coleman. www.anniecoleman.com. Relativity, the Special and General Theory by Albert Einstein. Continuing Part 2. Sections 21 through 23. Section 21. In what respects are the foundations of classical mechanics and of the special